Swayam Prabha. Digital India. Educated India.
Hello and welcome to the series of lectures on control systems. So over the past few lectures, as we've been discussing state space methods, and in the very last lecture what we've seen is something called similarity transformations. Towards the end we also connected this notion of similarity transformation as a means of simplifying this computation or this how to obtain this e to the AT matrix, right? Because we saw that e to the AT, unlike the scalar case where it just exists e to the power x as a function, the e to the AT matrix however is something that we have defined, because of its apparent similarity with the scalar counterpart. So in a sense that's by definition, by our choice, that we call it e to the AT. You could have called it something else as well, right? It doesn't really matter. The point is that we saw that if you have this matrix A which can be taken to a matrix say lambda through a similarity transformation such as this, then we have seen that this e to the AT can simply be written as t times e to the lambda t inverse, right. So this is exactly how we plan to go about this. This gives us a hint about how we can obtain this, in the sense that if this lambda matrix we have seen, if this is diagonal, that is if a matrix is similarly diagonalizable through a similarity transformation, then all that we need to do is to evaluate this, and this we have seen is very easy, right. So the diagonalization gives us a very good handle over this, in the sense that once you have the diagonal matrix, then you take Si minus this lambda, and take its inverse. The inverse of a diagonal matrix is very easy, just take the reciprocal of each entry in the diagonal. So you take 1 by s minus lambda 1 in that form, and then take the individual Laplace inverses, and you will only have n Laplace inverses to perform, because after all it is a diagonal matrix n squared in size, but only n of those entries are non-zero sitting on the diagonals. So you will only need to perform n Laplace inverses, right, and you get this immediately. So this gives us a very nice handle over this, and in fact with experience you will notice that this it's that performing the Laplace transform is not really a big deal, because after all if you get this in the diagonal form lambda 1 lambda 2 like this till lambda r, if this is your lambda matrix, then you don't really need to go through that Laplace inversion. You can immediately say that e to the lambda t is then going to be just e to the lambda 1 t dot 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 till e to the lambda r t. Now all this is well and good, but the question is, who is going to tell us that what these matrices T look like, which will indeed transform this matrix A into a diagonal form, and if we know what they will look like, how do we obtain them? So there I left it at that in the last lecture, saying that there is this thing called eigenvalues and eigenvectors, which you are probably familiar with. So what are eigenvalues and eigenvectors? We for example have this matrix A. So if you have a matrix A which is say n cross n, of course we are taking only real matrices here because this is not a linear algebra course per se, so we will only confine ourselves to the real field. This V is basically an n cross 1, and if you have a real lambda, so of course you can have complex eigenvalues, we will not consider that case now, there are ways of handling that, we will not consider that case here. Yeah, we will withhold that discussion. Yeah, we will only consider matrices that have all real eigenvalues. Yeah, then this is basically the equation that is satisfied, and we say that V not equal to 0 is an, of course if V is equal to 0, then this is satisfied anyway trivially. So V not equal to 0 is an eigenvector corresponding to eigenvalue lambda. Now it turns out that you do not necessarily need to always solve this in order to obtain lambda. The way to obtain lambda is you have another handle over this, right. You can just say determinant lambda I minus a, the characteristic polynomial, that is, you say determinant lambda I minus a is equal to 0 and solve. Yeah. So roots are eigenvalues, and once you have obtained these eigenvalues by solving this determinant, then you plug it in here and you put this matrix here V and equate this as an unknown, right, and then you will get your solution. Okay. So we will take an example maybe towards the end of this lecture, or maybe after we have covered this topic, and things will be clearer, right. So it turns out that why is this eigenvalue important in the context of diagonalization? It turns out that we have this important result, that this is not a both way result, by the way. So if a matrix A in R n cross n has n distinct real eigenvalues, then it is diagonalizable using a similarity transformation. Now there are a lot of involved nitty-gritties and conditions on this, things like so called algebraic multiplicities and geometric multiplicities of eigenvalues. We will really not get into that. I will just like to point out that this is not an only if condition, yeah, in the sense that even if a matrix fails to have distinct real eigenvalues, it may still be diagonalizable. So for the most stark contrast to this, or a counter example to this, consider the identity matrix. Yeah. So the identity matrix n cross n, what are the eigenvalues of the identity matrix? So lambda I minus I is equal to 0. If you put the determinant of this, you will see that the lambda is always equal to 1. Yeah. So this has n eigenvalues, all are equal to 1. All eigenvalues are equal, and yet this is already a diagonal matrix. So you take any T matrix, any non-singular matrix, converts it, of course there is nothing to convert, it is already diagonal, but then again any non-singular matrix converts it to a diagonal form, yeah, through. So this is basically a counter example to show that the reverse or the converse is not true. Yeah. So in case there are repeated eigenvalues, even then it may be diagonalizable. If there are distinct, then it is definitely diagonalizable. Yeah. If there are distinct real eigenvalues, then it is definitely diagonalizable. But even if they are repeated, you might still be able to diagonalize this. We will not talk about complex eigenvalues, because then you will end up with complex eigenvectors, yeah, and that matrix similarity transformation T, yeah, if you want to diagonalize it still, you might have to choose a complex matrix T, yeah, and those are not physically realizable, those do not have much significance either. Yeah, so that is why we will not be too interested in such things. Okay. So we have shown you that if a matrix has all its eigenvalues real and distinct, then it can be diagonalized. Even if it is not so, it may still be diagonalizable. However, in some cases, as we shall see, again through examples mostly, that you will not be able to diagonalize it, but there are still ways of getting as close to a diagonal form as possible, which will then enable you to evaluate the e to the at matrix with relative ease. Okay. All right. So through similarity transformation. Okay. So all eigenvalues here are equal, and yet you have plenty, not just a one similarity transformation, you can have plenty of similarity transformations. In fact, it is true that if for any matrix, for example, if you take, say, if T inverse AT is diagonal, then alpha times T whole inverse A alpha times T is also diagonal for alpha not equal to 0. This is also true, right? It is trivial for, so if you take a scalar multiple of that similarity transformation matrix, even that will diagonalize your matrix. Okay. The reason is obviously it's alpha T whole inverse times A times alpha T, yeah, is equal to nothing but 1 by alpha times T inverse A alpha T, and then you pull out this alpha and alpha 1 by alpha out because obviously they are scalars. So alpha by alpha T inverse AT, so this is going to be equal to T inverse AT, so that is also going to give you the diagonal matrix. So if you find one such similarity transformation which takes you to the diagonal matrix, then there are infinite number of such similarity transformations that take you to the diagonal matrix. Yeah. So the same, it's nothing exceptional, nothing special. The same is the case here as well. Here of course any non-singular matrix takes you, right, not just scalar multiples of that particular similarity transformation, any scalar multiple, any non-singular matrix here, if your matrix is identity to start with, even though it has repeated eigenvalues, any non-singular matrix converts it to a diagonal form through similarity transformation. So remember that bit. Okay. But now why is this true? We will see a very small sort of a proof of this. Yeah. So there are two things here. First, suppose you have A lambda 1 is equal to lambda 1 V1, A lambda 2 is equal to lambda 2 V2. Like this you have A lambda n is equal to lambda n Vn, where lambda I is not equal to lambda j for all I j, yeah, such that I not equal to j. So unless I is equal to j, lambda I is not equal to lambda j, that is what it means to have distinct real eigenvalues, and of course lambda I is real, we have assumed, for all I. Yeah. So now notice that if we write this in this fashion, sorry I have messed up, excuse me, yeah. So this is V1, this is V2, this is Vn, yeah. So then with this we can now write them side by side. So notice that this is n cross n, this is n cross 1, so you multiply them and you get this entire thing is also n cross 1, and on this side also you have n cross 1. Of course this lambda is just a scaling factor, so it does not alter the size of the vector V, the V1, V2, V3, they are just scaled multiples of scalar multiples of this V1, V2, V3. So what we can do is we can write them as columns of a matrix. Yeah, this is basically coming from Rn, right, because the net product n cross n times n cross 1 is n cross 1. So then this is AV2, and we have likewise AVn. This is going to be nothing but lambda V1 dot 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 till lambda Vn, right. This then tells us that we can pull out this A on the left hand side because it is, and we can write this as V1 V2 dot 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 till Vn is equal to, on the right hand side what I am going to do is, and I urge you to sort of verify that this is indeed the case, V1 V2 dot 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 till Vn, and then I take this diagonal matrix lambda 1 lambda 2 till lambda n. The key to this observation is the fact that when you take post multiplication, so when you take a post multiplier, this matrix is a post multiplier, no, this is what we call the lambda matrix, this is a post multiplier. Okay. What a post multiplier does to a matrix is take combinations of its columns or acts on its columns. So you now see this and you will immediately realize that this is indeed can be written in this fashion, right. So then we have, let us call this matrix as our T. So we have AT is equal to T lambda. We have come this far, but there is still something that is missing here that will prevent us from going one step ahead of this. What about this matrix T? Is it really non-singular? Because if it is non-singular, if it is not non-singular rather, then I cannot hit it with T inverse on the left because the T inverse would not simply exist. So I need to at least show that this set of eigenvalue equations, this eigenvalue eigenvector equations that I have written here, that these eigenvectors, basically what this statement says is that if it is diagonalizable, then that is tantamount to saying that I am at the last step now. The one missing piece in the puzzle is if I show that this T is non-singular, that is it is invertible, then I will be done, right. So that is all that needs to be shown. So in other words, I have to show, remember as we discussed in the previous lecture, that if a matrix is non-singular, then its columns as its rows are, so but we will here deal with the columns, so its columns are linearly independent, which means that if you take any non-trivial combination of the columns. What is a non-trivial combination? So basically then you take summation Ci Vi I going from 1 through n and take any such 0 such that there exists at least some I for which Ci is not equal to 0, yeah. So that is a non-trivial combination, yeah, that is called a non-trivial. So if you put all the Ci's to be equal to 0, then you will have equality by default, it is like an identity, yeah. It becomes an identity. If you take Ci to be equal to 0 for all Ci, for all I, then it is 0 on the left, 0 on the right. On the other hand, what we are saying is that if it is non-trivial combination, if it goes to 0, yeah, then Vi's are linearly dependent, which is something we do not want to encounter, right. So we want to show that if this there is a combination of this Vi's that goes to 0, then it better be the trivial combination, that is all the Ci's better be 0. If they aren't, then this Vi's won't be linearly independent. But we want to show that they are linearly independent. Why? Because if we show that they are linearly independent, the columns, then this T matrix will have full rank. If it will have full rank, as we discussed in the previous lecture, if it will have full rank, then its determinant will be non-zero, and the other way of stating that is that it is going to be invertible, yeah, which is what we want, because if it is invertible, we can hit this equation. Notice this boxed equation here, we can hit this equation by T inverse on both sides, and then we can get, so the question before us is, can we do this? Can we actually get a T inverse AT such that it is diagonal? So we have come this far, the only thing that we now need to ensure is that this T is non-singular. So how do we do that? So suppose we have summation Ci Vi is equal to 0, where without loss of generality you want at least one of them to be non-zero, no? So let us say, I mean I can choose C1, C2, C3, any one of them. So without loss of generality, let me say C5, because I like the number 5 maybe, yeah. So let us say without loss of generality C5 is not 0. The others also could be not 0, but at least C5 is not 0. There could be C5, C6, C7, C8 which are not 0. I do not care. I have found at least if it has to be linearly dependent, then one of them at least has to be non-zero. So let us say C5 is non-zero. Then what I do is this, that I hit it with A minus lambda 1 I times A minus lambda 2 I times dot 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 A minus lambda 4 I, and then I skip the A minus lambda 5 I, that term, okay. I write A minus lambda 6 I, yeah. So because I have assumed that the C5, or I have considered that this, at least the C5 is C5 is not 0, right. So that particular term which I know to be not 0, let me omit that particular term, let me multiply it with n minus 1 such terms, A minus lambda 1 I a minus lambda 2i, a minus lambda 3i, a minus lambda 4i, then I skip a minus lambda 5i and I continue with a minus lambda 6i, a minus lambda 7i till a minus lambda ni, yeah. And what is my hope that in doing so where will I get? So then notice Ci Vi is equal to 0 for I going from 1 through n, okay. So I'll go over to the next slide then, yeah, and I will observe immediately that what about a typical term like let us say C1 V1, okay. What happens to a typical term like C1 V1? Any term other than let us say C5 V5, okay. When it gets hit by a minus lambda ni, a minus lambda n minus 1 I like this dot 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 all the way till a minus lambda 1 I. In between remember a minus lambda 5 I is missing, yeah. So what does this term look like? Because if I see what C1 V1 looks like, I will see analogously that other terms will also look similarly. Notice when I pass this through first term here, so first I combine these two fellows here, what I then get is C1 times a V1 minus lambda n V1. But what is a V1? I know a V1 is basically lambda 1 V1, no? So therefore this in turn turns out to be C1 times lambda 1 minus lambda n V1, yeah. So then the next term acts on this. So then the next term acts on this, I get a minus lambda n minus 1 I times this C1 is sitting here lambda 1 minus lambda n times V1. But this part is a scalar now, so I can easily push it ahead here and I will get C1 lambda 1 minus lambda n times a minus lambda n minus 1 I V1. Now again what is this? Remember if I just pop this in here, this a V1 is again going to give me lambda 1. So this is going to give me C1 times lambda 1 minus lambda n times lambda 1 minus lambda n minus 1 times V1. So likewise I will get a product till I come to the last term where I get lambda 1 minus lambda 1 C1, then lambda 1 minus lambda 2, lambda 1 minus lambda 3 like this till lambda 1 minus lambda 5 is of course missing, but lambda 1 minus lambda 6 so on till I get lambda 1 minus lambda n times V1 is equal to 0. But now notice that this term is going to go to 0. So therefore this result, this when I act on this entire sum here, C1 V1 will vanish, yeah. When I act with this product of these n minus 1 matrices, so let me see the last one, so this I have probably mistaken here, 6, yeah, this is n, this is n minus 1. So remember in this product, if I have not mentioned here, a minus lambda 5 I5 I, sorry not I5, a minus lambda 5 I is missing. Whichever one I have considered to be non-zero, at least that C5 I have considered to be non-zero, so a minus lambda 5 I is missing, yeah. So now what happens then? Similarly what happens with C2 V2, yeah. You will see that you will eventually encounter a point where this lambda 2 minus lambda 2 appears, yeah. Instead of, you just replace lambda 1 with lambda 2 and you see this term will vanish. Then for C3 you replace this lambda 3 with lambda 1 with lambda 3 here, this term will vanish. So eventually all the terms other than C5 remain, yeah. You see that because there is no way C5 can vanish. Now when you hit it with C5, when you hit C5 on the other hand with C5 V5 with the same product of n minus 1 matrices, you will see that this, if you do not see it immediately, I am just writing the result, you just open it up and take it as an exercise and you will be immediately able to see that this is going to be lambda 5 minus lambda 1 times lambda 5 minus lambda 2 dot 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 till lambda 5 minus lambda 4, then lambda 5 minus lambda 6 yeah, lambda 5 minus lambda 5 is missing, because a minus lambda 5 I is missing in this product here, right. So the lambda 5 minus lambda 5 does not occur, yeah, then you get lambda 5 minus lambda 7 dot 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 till you get lambda 5 minus lambda n times V5, yeah. So this is the only term that remains, but now you have said that this entire thing is equal to 0 on the right hand side, so this must also be 0, this must also be 0, yeah, because every other term has, by my calculation earlier I have shown that every other term vanishes, yeah. So this must, so therefore why is this true? Since summation Ci Vi is equal to 0, therefore that product of all those terms with summation Ci Vi is also equal to 0. But now when you take products with individual terms other than C5 V5, they automatically vanish. So therefore you are led into concluding that C5 V5 and this product of this lambda 1 minus lambda 5 minus lambda 1 and all these, this must be equal to 0. But now notice that because the lambdas are all distinct, this is not equal to 0, this is not equal to 0, this is not equal to 0, none of these lambdas, none of these scalars are equal to 0, right. And we have also assumed that this C5 is also not equal to 0, and because V5 is an eigenvector, remember in the definition of eigenvector itself we said, right, in the definition of the eigenvector itself we said that this eigenvectors are generally non-trivial vectors, because the eigenequation will be satisfied by that 0 vector always, so anything can be an eigenvalue that way, that is not interesting. In order for something to be an eigenvector, it must be non-zero, that is the least we have to expect out of it. So now you see, you are having a product of all these non-zero numbers, whether they are scalars or vectors, yeah, and that turns out to be 0, that is impossible, right. So therefore must be a contradiction, therefore this is a contradiction and C5 must be equal to 0, because that is the only thing that we had assumed. See, V5 has to be non-zero if it is an eigenvector, that we cannot contradict, that is by definition. The premise of the thing was that all the eigenvalues are distinct, so if the eigenvalues are distinct, that also we cannot contradict. The only thing we can contradict is our assumption that C5 was equal to non-zero, but if we allow C5 to be 0, only then this is satisfied, so therefore C5 must be equal to 0. But what does that mean? Anything that you assume to be non-zero can likewise be shown to be actually end up becoming 0, yeah. So therefore every Ci, therefore it implies that summation Ci Vi I going from 1 through n is equal to 0 is the same as, this means that, so this means summation Ci Vi from I going from 1 through n is equal to 0 implies Ci is equal to 0 for all I, yeah, which is in other words to say that therefore this set of vectors, eigenvectors V1, V2 till Vn is linearly independent. So therefore eigenvectors corresponding to distinct eigenvalues, yeah, distinct real eigenvalues, they are linearly independent, and therefore this matrix T given by V1 till Vn is invertible, because it has full rank. If it is full rank, then its determinant is non-zero, if its determinant is non-zero, it is invertible. So therefore we have the recipe, we already saw earlier that we had AT is equal to T lambda, which is the diagonal matrix. So now we have T inverse AT is equal to this. So we will quickly take an example to show you how this method works. So let us say we have this matrix A given by, we have this matrix A given by, let us say 0 1 0 3 0 2 minus 12 minus 7 minus 6. I will not do the complete calculation, yeah, you do that complete calculation for yourself and find out what the eigenvalues and eigenvectors of this matrix are, okay. So I leave that to you to complete the exercise entirely. So you see that if you take determinant of lambda I minus A is equal to 0, this is tantamount to, I have already solved it earlier, so I will not go through that trouble. So you check, there is going to be lambda plus 2 into lambda plus 3 is equal to 0. So your eigenvalues are lambda is equal to minus 1, minus 2 and minus 3. So check, I hope my calculations are not wrong, but even if they are, you should be able to check, but the idea is to show you the method. So now you solving for this determinant of lambda I minus a, I got this, which upon solving leads to these 3 eigenvalues. Once I have got the eigenvalues, now my job is to get the eigenvectors, because the eigenvectors are the ones that will actually give me the transformation matrix, that similarity transformation matrix. Okay. So then, for example, I'll just solve one of the eigenvectors for you. You can solve the others. So let me solve the eigenvector for -1, the eigenvalue -1. So then you have 0, 1, 0, 3, 0, 2, -12, -70, -7, sorry, not -17, -12, -7, -6 times some vector. So let us call this v1, v2, v3, a 3 by 1 vector is equal to -1 times this vector v1, v2, v3, yeah. So therefore I have v2, when I operate 0, 1, 0 on this, I get v2. So on the left hand side then I have 3v1 plus 2v3, and finally I have -12v1 -7v2 -6v3, yeah. I hope that is what it is, and that is going to be equal to -v1 -v2 -v3. So writing these 3 equations, I have v1 plus v2 is equal to 0, that is my equation number 1. Second equation is well, 3v1 plus v2 plus 2v3 is equal to 0, and the third equation is -12v1 -7v2 -5v3. Am I right? Let us see. Is equal to 0. Okay. So how do I obtain a solution for this? This, if you have done a course on linear algebra, you would know this is like tantamount to solving for the kernel or the null space, yeah, the right null vector of a minus lambda I, yeah. But anyway, our job is here to kind of solve for these equations, and we will see that eventually this this matrix, this V matrix comes out to be, I mean, of course you can take any scaled version of this also, that will also be, because a vector, remember, if you are obtaining a vector, then any scaled version of that vector is also going to satisfy, yeah, that's the property, right. If a vector V satisfies something property, then alpha times V also satisfies that equation of the kernel, yeah, as we have already shown you earlier, that any transformation matrix you take, yeah, you can always cook up multiple transformations from that single transformation. So here also let us say this is what we have. So if we try to now kind of eliminate these things here, so we have v1 is equal to minus v2, and let us say we plug it in here in the second equation, then we get v1 is equal to minus v2, so minus 3v2 minus 2v2 plus 2v3 is equal to 0. So this is my first conclusion, and then this leads me to conclude that v2 is equal to v3. This is my second conclusion, and you will see that if you put it in the third, you basically get nothing new, yeah, you will get nothing new. You just plug in these conditions, these two conditions here, so you put in v1 is equal to this, it will be identically 0 on either side, yeah. That is typically how it is. So you have to deal with only n minus 1 of these fellows, yeah. So yeah, you can actually, as a matter of fact, you can check. So you can take minus 12 v1, and then v2 you replace with minus v1, so plus 7 v1, and v3 is v2, so it is basically minus v1, so you replace with plus 5 v1. Now that is going to be identically equal to 0. So this third equation is basically not going to help you much, yeah, it is not going to help at all. So you take any two of these equations and they will suffice. You could have chosen the first and the third, you could have chosen the second and the third, one of the equations is just going to identically vanish. But now this is not uniquely determined, as I said, so I will choose v1 is equal to 1, that is the 1 degree of freedom that I have, okay, you will have 1 degree of freedom here, and then automatically v2 gets set to minus 1 and v3 gets set to also minus 1. So my V matrix then becomes, let me use a different color, so this V matrix then becomes 1 minus 1 minus 1. So similarly, if you continue like this, you will see that for the eigenvalue 2, I can similarly obtain W is equal to 2 minus 4 1 such that AW is equal to minus 2W, yeah, and similarly U you can choose as 1 minus 3 3, yeah, that is how calculated, where you will have AU is equal to minus 3U. So please check these calculations, okay. So I might have made some silly mistakes. So in that case my T matrix turns out to be nothing but, I put them on the columns. So I get this 1 minus 1 minus 1, 2 minus 4 1, 1 minus 3 3, and immediately I can see that T inverse will exist because this determinant will not vanish, you can check. So what I obtained by my calculation was 9 by 2, 5 by 2, 1, minus 3, minus 2, again please be sure to check this, okay, do not take my word for it, it will also give you good practice. The idea is that I am going to discuss the method, not so much the nitty gritties of the calculations, that you should practice for yourself to get familiarized with this, 3 by 2 and 1, okay. So now if you take this e to the lambda t, yeah, you will see that lambda matrix comes out to be basically minus 1, minus 2, minus 3, 0. So e to the lambda t comes out to be nothing but e to the minus t, e to the minus 2t, e to the minus 3t, yeah, that is straightforward. So the main calculation is in basically obtaining these eigenvectors, that is what it is basically boiled down to. And finally, if you want to obtain e to the AT, as we have already shown you before in the previous lecture, you better just take t times e to the lambda t times t inverse, yeah. So I have not completed that calculation, that again you do for yourself, or maybe take the aid of MATLAB and check that this is indeed the t, the e to the AT, okay. So this is an efficient way of computing this. Now this immediately brings to mind a second question, like what if this is not diagonalizable? What can we do if it is not diagonalizable? Is there a way out? So for example, we have seen that although if the eigenvalues are not distinct, then it may still be diagonalizable, but there might arise certain situations where it is just not diagonalizable, it is just not possible, yeah. So for example, I will give you this matrix here, and I will give you this example, so you can actually check that this 1 1 2 1 1 2 0 1 3 0 0 2, alright. So if you try to work this out, you will see that the eigenvalues are lambda is equal to 1 comma 1 comma 2. So you will immediately see that there is a repetition of eigenvalues, but that does not still ring an alarm bell, okay. It may be just like the identity, this fellow also has repeated eigenvalues, but that does not necessarily mean that it will not be diagonalizable. However, now if you try to take a closer inspection of this, then you realize the problem. So you take this is your A matrix, so you take this 1 1 2 0 1 3 0 0 2 times this V1 V2 V3 is going to be equal to V1 V2 V3, yeah. So then you get 2 V3 is equal to V3 from the last equation, so that basically tells you V3 must be equal to 0. From the second equation you see V2 plus 3 V3 is equal to V2, but of course this V3 is already 0 as we know, so this is basically identical, V2 is equal to V2, it does not say much. What about the first equation? The first equation is V1 plus V2 plus 2 V3 is equal to V1, yeah. So what does this say? Yeah, what does this say, we wonder, right. So again this V3 we already know to be 0, V2 we know nothing about, but this V1 plus V2 is equal to V1, then it must imply that V2 is equal to 0, yeah. So then we have this V2 is equal to 0, V3 is equal to 0, and V1 can be anything. So there is only one way of cooking up a matrix, right. The moment I cook up a, let us say a V1 0 0, yeah, an eigenvector for lambda is equal to 1, that is the only eigenvector I can cook up. If I choose, let us say, another alpha times v1 0 0, yeah, this is actually a scaled version of this and therefore linearly dependent, yeah. So the set you check that alpha times v1 0 0 minus or minus alpha times v1 0 0 plus alpha v1 0 0 is equal to 0. So minus alpha times the first vector plus 1 times the second vector, yeah. So this vector and this vector, this gives you 0 where alpha is not 0 necessarily and 1 is also not 0. So a non-trivial linear combination giving you 0, which means that these are linearly dependent. So you fail to find two linearly independent eigenvectors for the eigenvalue 1 which is repeated twice, yeah. This is essentially the crux of the whole problem, yeah. So what do we do in such case? Do we just give up and we cannot diagonalize, so I mean just give up our hopes of doing anything with this, yeah? Well, not quite. So in that case what comes to our rescue is the so called Jordan form. Again this requires a detailed proof and a lot of discussions about the existence of this Jordan form, that it exists and that it will always work. It is a fascinating result which was discovered 150 years back in the 1870s, yeah, by Camille Jordan, yeah, the mathematician. But it is a beautiful result in the sense that, you know, if you go through the entire proof, which is probably part of an advanced linear algebra course, you will find it is fascinating the way things just fit in, yeah, the pieces in the puzzle just fit in like a jigsaw puzzle, right. But for now I will just give you the method. So this is one topic where I really do not want to be waylaid into trying to prove and give you more insights about Jordan form. Just suffices to say that there exists a proof that for every square matrix there exists a similarity transformation which takes it to its Jordan form. The special case where each of your eigenvalues are distinct, the Jordan form is basically the diagonal form in that case, okay. Even if it is not distinct, let us say for example in the identity case. So what I am trying to say is that diagonal matrices, so the Jordan form within it incorporates all of these. So the diagonal matrices are special cases of the Jordan form, okay. So I am not going to again go into the proof, I am just going to outline the method for you and then with an example I am going to show you how to get this Jordan form, okay. And that's all that I am going to do for this course at least, okay. So that at least you know how to work around and get this Jordan form, okay. Right. So here is how we go about it. So see, does not matter how many times the eigenvalues are repeated in this equation, the determinant, right. After all, even if there is one occurrence of this eigenvalue, there must be at least one eigenvector, because after all this entire equation comes from AV is equal to lambda V, so it must be satisfied for at least one V, yeah. So there must exist one eigenvector at least. Here there are two repetitions of the eigenvalue, or rather the eigenvalue is repeated twice, but I managed to find only one. The point is that you will always find at least one. If I had found two I could have diagonalized this. Unfortunately in this case I have found only one eigenvector corresponding to the eigenvalue 1, although the eigenvalue occurs twice itself. So what is the best thing that I can do? Here is how we generally proceed with the Jordan form, and here is the outline of the overall method, okay. So what we do is this: you take AV is equal to lambda V, let us call it the first time. So this is lambda V, lambda is the repeated, because remember if there is no eigenvalue that is repeated, then we do not need to get into all this business, then it is always going to be diagonalizable. So this problem only occurs, not always occurs when there are repeated eigenvalues, but can only occur if there is at least some repeated eigenvalue. If there are no repeated eigenvalues, then the question of non-diagonalizability does not arise, yeah. So suppose this is repeated, then I have this AV1, so find out how many linearly independent vectors satisfy AV is equal to lambda V. So in our case in this example there is only one such eigenvector, I have seen that, right. Once I have got this V1 0 0, see any vector that is in the, that is the eigenvector must satisfy this condition. This V1 can be anything, but now you try to cook up any other vector, it must be a scalar multiple of this vector, yeah. So therefore I cannot cook up any more than one linearly independent eigenvector in this case, yeah. So in general that need not be true. So suppose you have an eigenvalue that is repeated 10 times, yeah, and let us say you find 3 eigenvectors corresponding that satisfy 3 eigenvectors that satisfy this equation and they are linearly independent, yeah. So it need not always be 1, just because in this case we have found 1, it is a smaller matrix, 3 by 3 matrix after all, and the eigenvalue is repeated only twice. So if you found 2 eigenvectors it would be diagonalizable, so you found only 1, so it is non diagonalizable. But let us say there were 10 repetitions of the eigenvalue. So the eigenvalue was repeated 10 times, that is you solved determinant Si minus lambda I minus A and you found that the eigenvalue 1 occurs 10 times. But then you put in this equation, this eigenvector eigenvalue equation, and you find that you are only able to find 3 eigenvectors which satisfy this, okay. So then what you do is you put 3 dots, okay, for AV is equal to lambda V, okay. So here is the method, just pay very careful attention to this, okay. So what you then do is A minus lambda, A minus lambda I times V, lambda this squared, and equate this to 0, because see after all this equation is nothing but A minus lambda I times V is equal to 0, yeah. So you take this and you put this here, yeah. So I am just taking some arbitrary numbers, this could be 5, this could be 7, this could be anything, I am just taking here 3. The second time you do this you get 2, okay, and then likewise you continue, you get A minus lambda I times cubed times V is equal to 0, but A minus lambda I V is not equal to 0 and A minus lambda I squared V is not equal to 0, yeah. So now suppose you get 1. So then, so this need not look such nice, maybe let me just spoil the party a little, yeah. Let me just spoil the party a little, let me not give it such a nice structure, it looks like very symmetric, it need not be like this. So then beyond this point, now if you go for A minus lambda I q to the power 4 V is equal to 0, then you find that no solutions, and you of course restrict that. Of course these fellows which satisfied the earlier equation, they will obviously satisfy this equation, no, because now you notice what is this, this is after all nothing but A minus lambda I times A minus lambda I cubed V, yeah. So whatever V satisfied this earlier equation, by default it will satisfy this later equation, but we are not interested in those solutions, we are interested in something that is coming up new apart from what we have already obtained in the previous stage, yeah. So but we want A minus lambda I V not equal to 0, A minus lambda I squared V not equal to 0, A minus lambda I cubed V not equal to 0, yeah, and we find that no solutions, no such solutions exist. So this is all that we have got. So then we say that the Jordan canonical form will look something like this, and I will tell you in a minute or in a moment what the transformation in that case will be, okay, just hang on with me. So the Jordan canonical form that we are shooting for will look something like this. So I will have lambda 1 0 0 lambda 1 0 0 lambda, that is one chain. So there will be basically there will be 4 chains. So let me make that a little bigger, let me make that a little bigger. So there will be 4 chains. So then we will have lambda 1 0 lambda, that is another, then we will have lambda 1 0 lambda, that is another, and finally we will have 1 lambda sitting in the diagonal alone. Okay, that is it, that is exactly it. Okay. So what are these I mean sort of things that we are looking at? So you put these dots in the horizontal line like this, yeah, but when reading the sizes of these so called chains, you club them together in the along the vertical line. So this gives you a size 3, so this is the size 3 chain, this gives you a size 2, so a size 2 chain, this gives you another size 2, so another size 2 chain, and this gives you a size 1, so this fellow has to be just the diagonal, so the trivial diagonal block. So in case of a diagonalizable matrix, the Jordan blocks are all 1 by 1, but the general Jordan block looks like this. So although you notice that this is not exactly diagonal, this is as close to diagonal as you can get, and the good thing is that this is actually block diagonal, because the remaining entries here, here, all of these all become zeros. Okay, so that is why we like this Jordan form. So any matrix, it turns out, can be taken to this Jordan form. So this is how you read off what the sizes of the blocks will be. Now once you know what the sizes will be, how to explicitly obtain the vectors is the question. Okay, so then in order to do that, as before, you solve for a minus lambda I times v is equal to 0, yeah, and you get your vectors v1. So in this example, for instance, you got, let us say this as v1, v2, v3, v4. So you got 4 vectors, let us say v1, v2, v3, v4. So these are your eigenvectors. Okay. Now from this v1, you might try and generate a preceding fellow. How do you generate that? So let us say from v1, so let us say you take a minus lambda I, yeah, okay, let me be a little methodical about this. What we are trying to generate is basically a chain for this. Yeah, we do not know whether it will be generated by v1 or v2 or v3, this is not necessary, yeah, that this pattern will follow. So v1 might have a chain of size 2, v2 might have a chain of size 3, we do not know. So there is no way of knowing. How do we know exactly explicitly? When we only do the computation, that is only when we will realize what the chain sizes will be. Okay, so here's what we do. We basically take this a w1, yeah, this second fellow in the chain, a w1, and we write this as let us say this v1 plus lambda w1, yeah, and ask ourselves, do we have a solution to this? If we do, then stick together v1 and w1, yeah, and then at the next step you take a p1 is equal to now w1 plus lambda p1, and again ask, do we have a solution to this? If so, then you update your set with p1, yeah, and you keep on like this and till you encounter an answer yes to this question, that do we have a solution to this. So remember, in this equation this is known, in this equation this is known. What we are trying to evaluate is this p1 here and this w1 here. So it turns out that in this case, because there is a size of chain of size 3, so the maximum size you will get for any of those, starting with any of those vectors v1 is a size of 3, so it will terminate here. Then you start with, let us say, v2. So for example, you start with v2, then you get a minus lambda I v2 is equal to 0. Then in the next step you equate a w2 is equal to v2 plus lambda w2. So this is known from the previous step, yeah, and then you ask yourself, can you solve? If the solution exists, then you stick together v2 with w2, yeah, v2 with w2 like this, sorry, it should be a little cleaner, v2 with w2 like this. Then you take v3, Suppose with V3 you only get V3 and then you do not end up with anything, so V3 is a singleton, and then you start with V4 and then you go up to W4 and that is it. So now the desired matrix will be this, you take V1, W1, P1, yeah, and then V2, W2, alright, and then V3 I want at the last, right, I want this diagonal block at the last, so I will push V3 right at the end, I will pop V4 before. So I will put V4, W4 and then I put V3 last. So if I choose my T matrix to be like this, yeah, if I choose my T matrix to be like this, then I will exactly get my T inverse AT to be equal to that Jordan canonical form that I have just shown you here, this J, okay. So suppose this J, where of course the characteristic equation of this A is basically S minus lambda to the power 8, yeah. So there are 8 repeated eigenvalues and only 4 eigenvectors, yeah. So there are 8 repeated eigenvalues and only 4 eigenvectors. Now of course you can easily imagine that if this A matrix was even larger with more distinct eigenvalues, then you just stack up those eigenvectors side by side. So first you get the Jordan block like this. So remember the order here, this is chain 1, this is chain 2, this was chain 4, this was chain 3. The only reason I swapped chain 4 and chain 3 is because I wanted this organization where the sizes of these chains were in descending order. So I found that V3 is a chain of size 1, so I put it last, and V4 I found is a chain of size, so this actually changed here. In the course of my calculation I found that this was V4 and this was V3, so I just swapped their order.
Oh, my bad. I did say A minus lambda I squared times V is not equal to 0, but while writing I missed out the not equal to, so it should be not equal to 0.
Okay. So this is how you obtain a Jordan canonical form. When we come back for the next lecture, we will actually take an example, of course not of a big size because these computations are best done in MATLAB. We will take a Jordan form of a smaller manageable size where you will actually have just one chain, yeah, just one repeated eigenvalue and one chain. You will not have these multiple chains. This is the most generic version of Jordan canonical form. You can actually try reading up on the methods to obtain computationally a Jordan form, but we will just show you an example and hopefully that will make things a lot clearer. And then we will see another method of computing this e to the AT matrix, and that with that we bring to a close our journey into this, looking at what the A to the AT matrix looks like, yeah, or how to compute that. And we will take another interesting bit of a digression from the next lecture onwards into something that we have not dealt with thus far, because quite simply the transfer function model does not allow us to do that, that is time varying linear systems. Till then, take very good care. Thank you.